In this video, we will revisit the license check program from last time. You can get the same compiled 64-bit binary from GitHub, and you can also watch the last video where I went into more detail how to crack this simple program. I will show now different simple tools and techniques that exist to analyze a program like that to circumvent the license check. This should show you that there are a variety of different ways how to solve this challenge. The file command is very useful to check what kind of file you have. So, file on your binary says it's an ELF 64-bit executable for Linux. You can also do file star to get the information on all files in the directory. And it then also finds the C source code here, so that's very useful. Let's open the program in a text editor like Vim. As you can see, it looks very weird. I've introduced ASCII before, so you know that every character is assigned a number, but there are numbers that don't have printable characters assigned. If you look at the man page for ASCII again, you see, for example, value 0 to hex 1F are not normal characters. ASCII is also only defined up to hex 7F or 127. But because computers work with bytes, so 8-bit, this number can range from 0 to 255. And ASCII only has half of them. So all those weird blue values in Vim are such numbers that don't have printable characters assigned. You can also do a hex dump of the file to get the actual values. Hexdump -c license 1. And you can see that there are many zeros in this file. Hexdump displays them as dots, but in Vim they are the blue stuff. But when you look closely, there are quite a few meaningful strings in there. For example, right at the beginning, ELF, which is a magic value hinting that this file is an ELF executable. You can also find some strings to libraries such as libc, which defines functions such as printf and string compare. And here we also see strings we know, the check license, access granted, wrong, and the usage message. And also this weird looking AAAA Cyan 42 OK string. Remember from last video that there was a string compare in it? Might get the license key we enter compared to this string? Let's try it. Ooh, access granted. Indeed, the license key of this program was in there all along. There's a great tool called strings that is doing what we just did, just nicer. It will scan a file and print out all printable character sequences with at least a certain length. So let's try it with strings license 1. And there are our strings. Last time we used GDB to read the disassembly and also debug the program. This time let's just use object dump for the disassembly. Object dump -d license 1. You notice that this file has a lot of more code than just the main function. That is because the compiler puts a bit more stuff into the actual binary. You know, computers are a little bit more complex than they seem at first. But all this is just standard stuff you basically find in any GCC compiled binary. And usually only the user created functions like main are interesting to us. Object dump can be used to get a lot of more information about this program. Let's print every header with object dump and pipe it into less for easier navigation. So first it says the file is an ELF binary for x86-64 architecture. The stack is not executable, indicated by the missing X, which is interesting once we will look at classic buffer overflows. And maybe the last interesting info here are the sections. We can see where certain data will later end up in memory. Interesting for us here is the text section. This section holds our code and it starts at address 4004D0 and is hex 1E2 big. And if you check the address where the main function was, you will notice that it's in there. The other interesting section is RO data, which is the read-only data section. So our strings can be found in there. If you open up GDB and break at the string compare, you can check the registers. And one of those registers will have an address from this RO data section. You can print this address with x/s and voila, there's our key again. Let's have a look at another more active tool. It's called strace and it can trace system calls and signals. When I introduced programming in C, we used printf to print text. That was a nice function that we added to our program from the libc library. but printf is just a wrapper around a function that the Linux system itself provides. Linux itself offers many different kind of functions called syscalls. You can read more about them in the man page to syscalls. One of those functions is write, and write can be used to write text to the standard output, which we can read on the console. So let's execute the license program with strace. This first line is execve, which is the function that tells the Linux kernel to now execute this program, license 1. And then a lot of magic stuff happens that we ignore for now. And somewhere all the way at the bottom here, the code that I have written starts, basically the main function. And you can here see the write syscalls that were executed with the text that we know. That's interesting, huh? There's another cool tool called ltrace. Similar to strace, it traces certain functions, but this time it traces library functions. Functions like printf or string compare come from the libc library, so ltrace can show us their occurrence. So first you can see the printf, and then comes the string compare, and it shows us the actual strings it compares. So that also tells us how the license check works in a pretty cool way. Let's throw this file in a graphical user interface. I will use Hopper on Mac. As you may know, IDA Pro is very expensive, but Hopper is a great alternative which is actually affordable. Hopper sees that it's an ELF executable and it can automatically analyze it for us. It places our cursor at the function called start, and not at main. Like we've seen with object dump before, there are a few more functions created by the compiler, and this here is the real entry point of the program. But what those functions are doing is not important right now. We are only interested in the main function. So we can look for the main function in the list of labels. So here's our main function, like in GDB. Just a bit more colorful, and Hopper can also show us with arrows where our branches are going. At the end of the last video, I've already showed you the control flow graph, which you can access at the top right. And a very cool feature from Hopper is the decompiler. Decompiling sounds like it would simply reverse assembler code back to C code, but that is not easy. The compiler changes and optimizes stuff, and you just cannot simply reverse it. But Hopper can guess how it might have looked like. Sometimes it makes mistakes, but often it looks pretty good. So it shows us here how it checks if we have supplied a license key. And then it does the string compare, and it prints either access granted or wrong. So that's pretty cool. To the left you can also find a button to display all strings. And as you can see, it also found the key. When you click on it, it will jump to the address where the key is located. And xref stands for cross-reference. That means this address is referenced somewhere. We can follow that xref, and we can see that this is the assembler code where the address of the key is moved into the ESI register. This prepares the function parameters for string compare. Some kids may have the opinion that Mac users suck. To please them, we will install now Radare 2 by cloning the Radare 2 repository with Git. You might have to install Git with sudo apt-get install Git first. To install Radare, run sys install.sh and wait. Once it's installed, you can go to the license 1 program and open it in Radare with R2 license 1. You may remember this address from object dump earlier. This is the start of the text segment that contains our code. First run AAA to automatically analyze and autoname functions. Then use AFL to print all functions that Radare found. Each character in Radare means something, and with question mark you always get information about the characters you can use. So A performs analysis of code. A question mark shows us that we can append F to analyze functions. And AFL lists those functions. Makes sense, right? Okay, so AFL shows us that it found a main function. So let's change our current location with S to seek to the location of the function main. You can also use tab completion here. Now the location in those brackets changed. With PDF, we can print the disassembly of the current function. Like Hopper, it shows us the assembly with nice arrows where branches go to, and it created comments for us with strings that are referenced in there. You can also type capital VV to enter visual mode. This shows you a control graph view of this function. You can move it around with the arrow keys, and the blue border indicates that we currently select this box. With Tab and Shift Tab, you can select other blocks. When you have a block selected, you can move the block with Shift and H, J, K, or L. With P, you can cycle through different representations, for example with or without the addresses in the beginning, or this minimalistic view, which is useful if you have a damn huge function. And with question mark, you can display a help. The help tells you that capital R is the most important shortcut you will ever learn for Radare. So press Shift R and be happy. You can also use Radare like GDB to debug the program. To do that, start Radare with the -d flag. Seek to the main function, analyze all with AAA, and display the disassembly with PDF. Now place a breakpoint at the start with DB. Now go into the visual view with capital VV again. Like with Vim, you can enter command mode with colon, where you can type :DC to run the program. Now we hit the breakpoint 1, and if you look closely, you notice the RIP in the first box. This shows us where the instruction pointer currently points to. With S you can step instructions, but we should use capital S, otherwise we follow functions which we don't want to. So Shift S to step further. Ah damn, we didn't supply a license key, but you get the idea. I hope this helps you to explore more tools and techniques, and remember that no tool is better than the other. They all have different features and representations of information. It makes sense to master them all. Except Radare. Some say that Radare is best, but nobody ever masters Radare.